Okay, so welcome to Dynamical Systems. I think this is still a continuation of Lecture 5. What we're going to do today is we're going to transition from looking at one-dimensional systems, which was basically the introduction, to looking at two-dimensional ones. And before we look at two-dimensional ones in detail, I'm going to take an approach that's slightly different from Strogat's. So this particular lecture has to do with the notes on linear systems. If you go to the website, you'll see there notes that I made on linear systems. It basically incorporates everything Strogat's is going to do for all dimensions. So I'm going to do the general theory now because it's useful and you use it at many other places as well. And then as we go through the specific examples in Strogat's, the two-dimensional ones, the three-dimensional ones, you'll see that it all actually basically comes back to this type of analysis. So this is the non-graphical part of the lecture, okay? And it's general results that I've collected over time and that people use whenever you integrate differential equations on a computer, usually approximate it as a linear system plus other stuff, and then you use these results. Whenever you do statistics or engineering, you basically have a linear system. Most of engineering is just studying linear systems in a systematic way. So then this general solution that I'm going to give you is actually applicable there. So that's why I made the notes. It's something you can keep, and it's very compact. So what we're going to do today is look at just systems with constant coefficients. In other words, what I have is basically x dot equals to a times x. In this case, x is a vector, an n vector, and a is an n by n matrix. So this has got quite a lot of linear algebra to do. You may have come across it in your second year. You should have. But I'm just putting it all in the same notation, and I think I'm adding something. I don't think you did the full general thing your second year. So if it's familiar, get yourself fit. It's review. But it's very, very useful to have. Okay, so A is an n by n matrix, and it's contained just of constants. So that's our definition of a linear system. And what we want to do is we want to solve this equation in general for any A. And the amazing thing is we can actually do it. Okay, and the way we go about it is to use what we know about A, the linear algebra properties, and in particular, we want to look at the directions of A that remain unchanged, because those directions will actually give you solutions that are just one-dimensional again. Okay, so we're going to convert this n by n matrix equation to n one-dimensional equations by using the properties of A. And the properties we use is we compute the Eigen System of A. Okay, so if you want to just recall what an Eigen System is, we define a vector, Ci, to be an eigenvector of the matrix A with eigenvalue lambda if it obeys the following equation. Okay, so this you should know from your linear algebra. You basically seek a vector such that A times the vector is just a constant times the vector. So when you apply A to that vector, you get the vector back just rescaled, but you haven't changed the direction. And this idea we then carry through to our differential equation in a very cute, nice way. Okay, and another way to write this eigenproblem is basically this A minus lambda times I, which is the identity matrix. C is equals to 0. And then we have that this is true, and we're looking for non-trivial C. This is true if and only if the determinant of that thing vanishes. Okay, and that then gives us the characteristic polynomial of A. So we want to find all the lambdas such that this determinant vanishes, and what we then get is that the determinant of A minus lambda I is equals to 0. This is a scalar. If A is n-dimensional, it turns out to be an n-dimensional polynomial, and you're going to see that in the examples that we do. For this course, we're going to just use two. We're going to spend a lot of time looking at two-dimensional ones, and then in the end, when we start looking at chaos, we're going to look at a three-dimensional example. Okay, so this equation This determinant that A minus lambda I is what I call the characteristic equation. Other people call it other things. But it's a characteristic equation for lambda. It basically gives you a polynomial that is of degree n, and I can write the polynomial in this way. So if you have a second order equation, you're going to have like lambda squared plus b lambda plus c is equals to 0, and you can solve explicitly for lambda. If you have a three-dimensional one, you can have a cubic equation for lambda. Okay, so I'm hoping this is familiar to you. Any questions at this point? Okay, cool. Right, the roots of this equation, in other words, solutions of this polynomial, is what we call the eigenvalues of A. They obey basically this property that that thing is equals to 0. So typically what you can have is you can either have n different eigenvalues, okay, and if the eigenvalues are different, then there is one eigenvector that corresponds to each eigenvalue. So the moment you have an eigenvalue lambda, you can actually go about and find an eigenvector that obeys this. That's always possible. What is more tricky is that if you can have an eigenvalue that appears twice. So suppose you have x squared, you'll have a characteristic polynomial that's like x squared minus 4, right? Then your eigenvalue is 2, okay? And it can appear twice because, if you have a characteristical polynomial that is x minus 4 squared, that's it, then the eigenvalue appears twice, the root is double, and then you have a problem because you're always guaranteed to have one eigenvector for every eigenvalue, but you're not guaranteed to have another one. So you can have a matrix that has the same eigenvalue, but it only has one eigenvector. Okay, I'm just saying the possibilities, and you'll see why this becomes important on the next slide. Okay, so if the eigenvalue appears more than once in factoring the polynomial, we call it multiplicity 2. So in other words, if you have a polynomial that is x minus 4 squared, then you have multiplicity, then the eigenvalue 4 has multiplicity 2. Yes?
X minus 4 squared, I think solutions are minus 4 and 4.
Sorry, that's my, you have x minus 4 squared. Okay, okay, so that one, this one has multiplicity 2, yes. And x minus 4 squared has multiplicity 1. Okay. So thanks for clarifying that. Okay, so now we know what the multiplicity is. Let's go on and say there's at least one eigenvector that corresponds to a particular eigenvalue. So for both those different polynomials, you're always going to have one eigenvector corresponding to the eigenvalue. Well, there you're going to have one eigenvector corresponding to the eigenvalue 4. Here you're going to have one eigenvector corresponding to the eigenvalue 2 and a different one corresponding to the eigenvalue minus 2. So the bottom polynomial is actually easy because you have two different eigenvalues. So you have two different eigenvectors, so you're done. The top one is more tricky because you're only guaranteed to have one eigenvalue, one eigenvector per eigenvalue. There's nothing that guarantees you're going to have two separate ones. Okay, and that's going to be a problem that comes in later. Okay, and there may be up to m independent eigenvectors. So this is where it becomes tricky, is that there can either be one or there can be two. It depends on what A is, but there's no guarantees. And the case where there are fewer eigenvectors than multiplicity is what we call a degenerate case. Okay, so I just wanted to get you all the definitions out there before I start handling them. Because the thing that I'm going to give you for the solution is the solution for everything. Okay, so it's complete. It's very nice. I said in one of the first lectures that linear problems you can solve completely, and I'm going to give it to you now. Okay, so those are just the definitions. Whenever you get a linear system, the first thing you do, regardless of what's asked, basically, is you work out the eigenvalues, which you get from the characteristic polynomial. Once you have an eigenvalue, you basically find a solution to your eigenvalue problem, and once you get, and then you can maybe, if you have a unique eigenvalue, you're done. If you have an eigenvalue that appears twice, you try and find a second one. It may not always be possible. Okay, so that's that. Okay, so now I'm going to give you the general solution, or the general means of finding the solution. And the first thing you do is, let's suppose, to write everything down, A has a set of k linear independent eigenvectors. So I've still got the general case. So I'm assuming k can either be n or it can be less than n. And that's always possible. Okay, what we're now going to do is we're going to construct a matrix P. And the way we construct P is we make its columns to be the linear eigenvectors itself. Okay, so, and D is going to be a diagonal matrix that has the eigenvalues on it. Okay, so what we're going to have is we're going to have P, which is the eigenvectors arranged as columns, and then we're going to have our matrix D, which has the eigenvalues in it. Okay, and so now if K is equals to N, P is square and invertible. That's also a result you would have seen in linear algebra. You'll see heuristic when we start using it, why it is so. Okay. And so here we have what P is. Okay, so P, you basically have P being the eigenvalues, C1 to 6K, and we have D, just to write everything out, to be that matrix of this is eigenvectors, the eigenvalues just on the diagonal. And so you must be careful. The first eigenvector must correspond to its eigenvalue in D. Okay. And so you have these two matrices. And then just the second statement is, I'm not going to prove it, but you'll see how it becomes true, is that if K is equals to N, in other words, you have as many eigenvectors as you have dimension of your matrix, then this thing is square and invertible. Okay, that you can prove. I'm not going to prove it. Okay, so now the thing is, once you have these two matrices, you must note that it is always true that A of P is equals to P of D. And the way you can see that is suppose you simply apply A to the first eigenvector, right? It simply equals to lambda times the eigenvector itself. So you get this eigenvector back, and you multiply it by lambda, but you've got to put D behind. So you simply are multiplying that thing. So if you look at it component-wise, this expression is always true. Okay, and it just comes from the properties of eigenvalues, and you don't even need, you can do it for any P, for any K. So P doesn't have to be square and invertible. If you have N is like 3 and P, and you only have 2 independent eigenvectors, this thing is still true. Okay, because it stems only from the property of what an eigenvalue actually is, or what an eigenvector actually is. And now we go to solve the differential equation, because this is where we use this property. To solve this differential equation, we want to solve x dot is equals to A of x. So what we're going to do now is we're going to say, let us substitute. We make a guess at the solution, and we assume the solution is basically P, which is this matrix of constants we've made out of the eigenvectors, times y, which is a new variable. Okay, and we can see that since the elements of P are constant, in order to use this thing, we need to compute the derivative of x. We have that x dot, you have the product rule, but the derivative of P is 0, so it's simply P times y dot. And so when we do that, we simply have that x dot is equals to p times y dot, which is equals to a times p of y. Okay, because I've replaced x over here with p times y. And then, because I know this property of that's true for any k, regardless of you have a full set of eigenvectors or not, I replace AP with with PD, and what I'm left with is P times, so I've moved these two onto the same side, so I basically have 0 is equals to P times y dot minus dy. And that's very useful because I know that P, the eigenvectors of P are independent and they're non-zero. So for every single eigenvector of P, this thing must hold. Okay, and so this expression can only be true if the thing in brackets is actually 0. Okay, and here's the reason. Since the columns of P are linearly independent and non-zero, we must have that y dot is equal to dy. So we're now getting a differential equation for y rather than x, but it is a much easier differential equation. In fact, it's a set of one-dimensional differential equations, because note that y dot is simply the new variable, and D is a diagonal matrix. So it's simply y1 is equals to some constant times y1 and nothing else. And y2 is equals to some different constant times y2 and nothing else. Okay, and so that thing becomes easy to solve component-wise. We write that solution down, and then we multiply it by P, and we have a solution for x. Okay, so it's easy to solve component-wise since D is diagonal, and then for each component, you simply have the differential equation that y dot is equals to lambda of lambda I yi, where lambda I is the differential equation, is an eigenvalue, and you can actually solve that, integrate that directly, and that's simply y is just an e to the lambda t minus t0 y0. Okay, so it's just an exponential growth that you get for every single component. Okay. So we've basically, by doing this transformation over here, we have simplified the problem, the sort of time-dependent part of the problem we want to solve, to one that's one-dimensional we can actually write down. So now we have the y's. You have an explicit expression for the y's, and these constants that appear in front of here are simply the value of the y at times t equals to 0, and they're constants. Okay, so all the solutions are simply exponentials with a certain growth factor and a certain constant in front, and that's it. And so a way I can write this in vector form, and last time I got into trouble for this, but I thought I would still show it to you, is I could write this thing. So these are the components now. Here I have written the vector form. Okay, so I can write it this way. It's basically, this thing is a matrix times a lot of constants. Okay, people didn't like that because they said, what have you done? You have made an exponent of a matrix. Do you guys know what that is? Oh, okay. So you can actually do this. There are rules to it. The exponent of a matrix is simply, you can view it as the Taylor series expansion of the matrix. So if you construct a matrix out of the identity plus a squared, the matrix squared, times, you can basically take a Taylor series expansion of that thing and get the answer. Okay? Be very careful when you see things like this. I'm not cheating. There is a formal way of dealing with these things. And you'll see it in textbooks and stuff. But just know that if your matrix is not diagonal, then you must be very careful, and you must actually go and find out what the definition is. For our case, because the matrix is diagonal, it's simply the same thing as saying that. Okay, so I just put this because if you go and look at advanced textbooks, you'll maybe see something like this where you have the exponent of a matrix. Know that you can evaluate them, but know that it's not a straightforward thing. But if the matrix is diagonal, then you can just be doing this. Okay, so it basically means for each component, it's just e to the lambda I t minus t0 replaces that. So this is just a shorthand way of writing out what I've written in the component form over there. Okay, so now we have y, right? And we can go back to this, use this expression, and we've proved that if we write x this way, we solve the differential equation. That's how we constructed y. But y may not be full. In other words, we have basically got, by using this construction, we have k independent solutions to the problem x dot equals to ax. Okay? And the way we do that is we simply take y and we multiply it by p. So I take the y that I've constructed over here and I multiply it by p. If you're not comfortable with this thing, let me just write it out what it means in full. And this is the second one that I'm going to recommend you use. And it also gives you a lot of insight. Okay. So what this is p, remember, is the vector of eigendirections. Okay. So what this thing is basically, and each component of this exponent is simply y0 e to the lambda of t minus t0. Okay, so that's the component times the eigendirection. And this result gives you actually quite a deep insight, not an insult. It would be an insult to view the insight as nonsense. Okay, it gives you quite a big insight into the solution. Because what it tells you is the solution of this linear system can be actually made of the sum of solutions to one-dimensional systems, provided you look along the eigendirections of your matrix. So what the eigendirections do is they give you directions in your system where the solution doesn't care about anything else at all. It just cares about what's happening on it. And by combining those, you can actually get the full solution. So it gives a very intuitive insight to what solutions to linear systems are if you've got the eigenvalues. Okay, so this is now the full solution. You're going to have a lot of practice in the next week or so looking at two-dimensional systems. We're going to look at all the possibilities that are there, basically, because it's so important. It sort of puts the foundation of solving the linear systems, but we eventually use what we learn from those to solve the nonlinear systems as well. It's a very, I think I like this part of the course very much because you go past one dimension. It's a very intuitive way of looking at it, and you can do a lot with it, and it lays the foundation for everything else. So as I said, 2 dimensions is the last time we're going to be able to integrate the equations exactly, because in 3 dimensions we start getting chaos. But we're going to get a very good intuitive feeling for what these things actually mean. And you'll see the eigenvectors coming in, and you'll see the solution moving along the combination of the eigenvectors as we write down the answers for several examples. Okay, so just to complete this, so this is if you have k independent solutions. So we have k independent solutions, but there's a theorem that you would have done in your second year that, or I hope you did in your second year, that basically says, if you have an n-dimensional ordinary differential equations, there are always n independent solutions. Okay, and that remains true. I think you shake your head, so you've seen it before. Okay, so we've now got k of them, and we want to construct the other solutions as well. And the way, this is where it gets tricky. If we start and we have k is equals to n, we are done. If otherwise, we must construct n minus k more solutions. And the way we do that is also kind of cute. And we'll do it on the next slide. So let's have a look at this. We're back to our linear system. We want to look at the degenerate case, because remember, if we don't have all the independent eigenvectors, then we effectively must have a differential equation that looks like that 1 minus x minus 4 squared, that x minus 4 squared, where two of your eigenvalues are the same. That's necessary. And then that may or may not have two eigenvectors. And if it has only one, it's degenerate. And that's what we're going to look at now. So we're going to say, suppose we have an eigenvalue that is degenerate, and it has multiplicity m. So it basically appears m times that particular eigenvalue. And there aren't a full set of eigenvalues associated. In other words, there are d, which is less than m, eigenvalues associated with it. In other words, in the two-dimensional example, it would be, suppose you have an eigenvalue like that appears twice, and so it has multiplicity 2, and it has one eigenvector associated. If it has 2, you can just do what you did in the previous case. If it has 1, you have to apply this. So what we have to do then is we have to construct the extra solution. And the way we do it is to find another vector that is not an eigenvector, but it's a family of the eigenvector. So let's call our eigenvector associated with this thing, the one we've got, let's call it that one, and we know the eigenvalue is lambda d. So what we're going to do now is we're going to construct another vector that's not an eigenvector, and we're going to say it must obey this thing. So remember, if it was an eigenvector, that would be 0, but it's not. It's a different kind of vector that obeys the same matrix multiplying it, but it's now equals to the original eigenvector. Okay, so it's a construction, and you're going to do this construction whenever you have a degenerate case. So the moment you get a degenerate case, in other words, you have two eigenvalues that are the same, you only have one eigenvector, you immediately go and you construct another vector using this rule. Okay, so what we're going to do now is we're going to say, we're now going to prove that if you construct another solution that is just e to the t minus t0 times t, which is your original eigenvalue, plus this new eigenvector, then that's a solution to your problem. And so this is basically an ansatz that we're going to prove that it works. But just notice the structure, right? You take your original eigenvector that you know, you multiply it by t. So you know for sure it's not the same as the original solution. Okay, so you know you've got a different solution from the original one, and then you add this extra eigenvalue, or this, not eigenvector, this extra vector, and then you're done. And to show you how it works, to prove that it solves this, let's simply work out. So if you now work out the derivative of this little beast, okay, the first thing you do is you take the derivative of the exponent, so that is just lambda d times the exponent times this vector, so this is the first term over here. Okay, so that's the derivative of the exponent times whatever's left, plus the derivative inside the brackets, so the derivative inside the brackets is just xc0d plus xc0d. Okay, so that's the derivative I've worked out. Now we've got to prove that that is equals to A times, or sort of the matrix A applied to this vector or the solution, and in fact it's true. So if you take A times xd, you take out the exponent immediately because it doesn't care. You take t out because that's just the scalar. So A times applied to cd of 0, this is your eigenvector. So that's just equals to lambda I. Okay, and let's see how much I wrote. Okay, so that's the first one. Okay, so this is still the first step. So you simply apply A to this top vector. So you have t times A applied to this eigenvector plus A applied to the new vector you've constructed. You multiply this thing out and you use the definition given up here. Okay, so the first one is just the eigenvector. So this thing is just lambda times CD. The second one, you simply use that expression over there. Okay, so the second one, so there's your eigenvector. The second one is just A times C1 is just lambda T times C1 from that term, plus your eigenvector over there. And what you can now see is that if you've done it, these two are the same. Okay, so you actually have a new solution that's been constructed that is different from the original solution. And it solves the problem. Okay, so you can fill up you can get new vectors like this and fill up until you get the solution complete. And this type of trick works always. So in the case, if you had, for the example I gave you, if you had multiplicity 2 with one eigenvector, you only have to construct one additional solution and you're done. But you can have, in 3 dimensions, you can have one eigenvector appearing 3 times, one eigenvalue appearing 3 times with multiplicity 3, and you can also only have one eigenvector. And then you have to keep going. Okay. So in the case that I've just given you, where you have more things, the more sort of a bigger multiplicity, so multiplicity bigger than 2, and you only have one eigenvector, you can repeat this trick, but you keep constructing additional vectors using the following definition. You make like a chain. Okay, so you start with your eigenvector, then you get your next one, C1, that just solves this, but is equals to the eigenvector. And if you had to construct C2, you just do the same thing, but you put a C1 in there. So you get the next vector from the other one. And then you can also prove that, okay, so I've just made the recursive. So this is basically a recursive thing. You can then show that if for all the vectors, if you construct it in this way, you can actually construct independent solutions. Okay, and the independent solutions are merely your eigenvector, the original solution, plus a sum. It's like a power series sum of these new vectors you've constructed. So the thing is, you always multiply it with t. So if it's your first vector, then it's just linear, so it's t to the 1. For the next vector, you multiply it by t squared. And you're multiplying, you have your new vectors always the constant, and then the previous vectors you multiply by t. So if you having a multiplicity that goes to, say, 2, you're going to have, instead of over here where you had your linear term in front of the 0, you're going to have a t squared in front of the 0. Okay, so there's a very definite structure. So, for example, now I'll write out the 2-dimensional one. Okay, so the first thing I'll let me go. If you write this thing out, I've just given you the formal solution here, then you can show that it solves this thing. And I don't know, it's the same way, exactly the same way that we proved this one, is you can simply differentiate this thing using the derivatives of t over here and multiply it by this matrix and repeatedly apply the definition of your eigenvalues, and you can prove that it solves it. Okay, but I'm not going to, I don't think I'm going to do that because it's going to put everybody to sleep, more so than you already are. Actually, you're not all asleep, so it's fine. So just to give you an example, if I is equals to 2, so in other words, you need to find 2 eigenvectors, then the solution looks like this. So it's still the exponent in front. Now, instead of putting just your initial eigendirection, you now have a t squared. That first thing that you constructed from that expression, you have a t in front of it. And this other one, the new vector, the final vector that you've constructed, you just have as a constant. So you can once again see that this solution here is independent from that one because it has a t squared in front of the vector. So you guaranteed independence, and you can prove that it's a full solution. So so basically, all the solutions have the form that you have an exponent in front that comes from the eigenvalue, and then you have this polynomial of things that are constructed from the eigendirections. Okay, and that will solve absolutely everything. I've now basically given you the way of finding all n independent solutions for your problem, so all linear problems can be solved. Okay, I did write out how you actually prove that the one solution, that it solves all of them, and I'm going to quickly go through it, but not in great detail, just so that you have it and that you know it's there, and that if you one day work with this stuff, it's actually useful to have the theorem, because a lot of the ways that you construct the things you can get from the theorem, and it's a check as well. So here's the solution. Here's the definition of how you've constructed the vectors, and then you basically go ahead and you work out the dot of the solution. And the first thing is you basically have the dot applied to your exponent in front, so that gives you the first term over here, and the second term you basically have the dot applied to that t, so that gives you the -1 going in there. And then you have to have A applied to this top solution. So you basically, the first one is easy. It's just lambda d, I use that definition, plus c minus 1 lambda d from there. And then you do the same thing and you simply apply A to these things, to the one in there, and you repeat that definition. So there you have it. And what you now have to do, the tricky thing, is to show that these two things are in fact equal. And the reason it's tricky is that in order to show that they're equal, you've got to compare these exponents that are the same, and here you've got an c minus 1. So that's what you're going to do. You can actually do the proof formally for all the cases, and I don't require that you actually can do this, but I just want to show you the trick, is that you must actually subtract the 2, okay, to find out what you want, and then you get something like this. Okay, you have c to the k minus some sum of c to the k minus 1. And the non-trivial step in the proof is basically you must change the summation index from k to k minus 1. So if you've done sequences in series, I think you've been exposed to this type of thing before, but you must just do it very, very carefully, and then you can actually prove this thing as well. Okay, so in the second term, we're going to change the summation index, and we're going to add the third term back. Okay. And then what you get is something like this. Okay, so you change the summation index, you let k prime goes to k minus 1. When k prime goes to k minus 1, right, you're going to have an I minus 1 over here, and that's what I meant. Sorry, an I minus 2 over here, and that's what I meant. You've got to add this term back in there. And when you do that, you can actually show that the two are equal. I haven't done it slowly. If you're interested in this stuff, keep it. It's useful. You use it in statistics, you'll use it everywhere else. So it's useful to at least follow my steps carefully, what I've done. But needless to say, you get the right answer, and so the thing that we've constructed is true for all parameters, or for all dimensions. And so we can always construct a full set of linear independent solutions to this problem. And just to tell you where we're going to be seeing it in Strogatz is, okay, so you can always construct a full set of linear solutions for eigenvalues with multiplicity greater than 1, so therefore every single case that we have. And in Strogatz chapter 5, which is what we're going to start tomorrow, or at least give the intro to tomorrow, is when we do with two-dimensional linear systems. And in three-dimensional case, we're going to start seeing chaos, but we're going to use this analysis again. So that's it. Lecture tomorrow in class, the first hour. Try the one problem. I only asked you to do, I gave you two problems. The one is just to practice, and the other one is to hand in. and because I want you to sort of focus on it and try and solve it on your own and actually look at it. Come and try it today already, and come and ask me if you get stuck with it. Okay. Okay, see you tomorrow at 3.
I have a question.
Yes.
I've been watching so many documentaries on chaos.
Yes.
And I don't get why statistics still shows up if something like chaos exists.
There's a very close connection between statistics and chaos. Let me just kill the video.